Experiment 3. In this experiment, we are going to use a fixed mass of gas and study the relation between the volume of the gas and temperature T of the gas at constant pressure P. The procedures are: first, insert a thin mercury index into a one-end closed uniform capillary tube. Second, put the tube in the water bath and finish the setup zone. Third, heat up the water by a Bunsen flame. Fourth, use a thermometer to record the water temperature T and use the half-meter rule R alongside with the tube to measure the length of air column L at regular time interval. For the precautions of the experiment, we have first one, the position of the thermometer. It should not touch the bottom of the beaker. Second, the use of the stirrer. The stirrer is used to stir the water regularly so that the water temperature is uniform. Next, what is the position of the mercury index inside the capillary tube? The mercury index should be put at the positions below the water level, such that the temperature of the gas inside the capillary tube is uniform. Next, why we use a uniform capillary tube? The reason is that for a uniform capillary tube, the volume of the gas inside is equal to the cross-section area times the length of air column, which is proportional to the air column's length, because the area, the surface area, the cross-sectional area inside the tube is uniform. Yes, for this reason, how does the volume of gas inside the air column relate to the length of air column L? Obviously, volume proportional to length. Okay. Why and how to ensure that the readings of L and T are taken at constant pressure? To ensure that the readings are taken at constant pressure, we should switch off the heater and stir the water before a reading is taken. The last things for improvement is we use thin water glass, thin water flasks, because we want to increase the sensitivity of the experiment. For thin water flask, the temperature of the gas inside is almost equal to the temperature of the water outside, which is recorded by the thermometer. The experimental results for T and L can be tabulated in a table. We have different sets of reading: first, second, third, and fourth sets. And we plot a graph of the length of air column L against temperature T in degrees Celsius. The experimental result for 4 sets of data, when plotted, they all lie on a straight line or almost lie on a straight line, and we extend this straight line backward to the point where L equal to 0. For this, the temperature is called absolute zero at this point is about negative 273 degrees Celsius if the experiment is very accurate. The result shows that the length of air column is variously linearly with temperature in degrees Celsius. The temperature in degrees Celsius scale Tc is now converted to the absolute temperature scale Tk by the conversion you have learned before. Tk equal to Tc plus 273. For example, if T1 originally in degrees Celsius is equal to 20 degrees, then in Tk it should be equal to 20 plus 273, which is equal to 293 Kelvin temperature. After the conversion, we plot a graph of length of air column L against temperature T in Kelvin scale. Then we have the x-axis becomes temperature in Kelvin, and at this point the temperature becomes 0K. At this point the temperature becomes 273K. And then we have the x-axis is the new one, and for the vertical axis the length is moved to this point. Okay, the vertical axis is moved to the point passing through 0K, and the new graph will be like this one. From the graph, we know that the length of air column is proportional to the temperature in Kelvin scale. That means length is proportional to this is absolute temperature. The length is proportional to absolute temperature of the gas. Or we can write down L1 over T1 equal to L2 over T2, etc. Notice that T1 and T2, the scale is in Kelvin scale. And because we have learned from the experiment, we use a uniform capillary tube, therefore the volume of the gas inside is proportional to the length of air column. Therefore, we have V1 over T1 equal to V2 over T2 again, and this equation is useful for calculation when the gas is fixed mass and it changes its volume and temperature under the condition of constant pressure. Notice that the temperature is absolute temperature. The unit is in Kelvin. Spend some time to read question number 1 and number 2. When a gas is heated, the speed of the gas molecules increases. Therefore, the gas molecule will hit the container wall more violently. Therefore, the gas pressure will increase. To maintain constant pressure, the gas molecules must hit the container wall less frequently. Therefore, the distance between the gas molecules and the wall must increase, which means that the volume of the gas must increase. Fishbowls contains a lot of air inside. When the fish balls are cooked, that means they are heated, the air inside expands. It implies the volume of the air increases. That means the density of the air inside decreases. On the whole, the density of the fish balls would be smaller than the density of water. Therefore, the fish balls float in water. Spend some time to read question number 3 and number 4. At temperature T1 equal to 20 degrees Celsius, let the volume of the gas be V1. When the temperature of the gas T2 equal to 60 degrees Celsius, let the volume of the gas be V2. Since the gas is heated at constant pressure, we apply the equations. We have V1 over T1 equal to V2 over T2. We have V1 over, remember the temperature should be at degree Celsius changed to Kelvin temperature. Therefore, T1 is 20 plus 273. V2 over T2 changed to Kelvin temperature, which is 60 plus 273. Therefore, V2 over V1 equal to 333 over 293 equal to 1.14. The percentage change of the volume is equal to V2 minus V1 over V1 times 100%, which is equal to V2 over V1 minus 1 times 100%, and the answer is 14%, which is an increase in volume. For number 4, T1 21 degrees Celsius, V1 100 cm cube, T2 equal to 88 degrees Celsius. The gas is heated at constant pressure, and assume there is no leakage of gas, which means the gas is heated at constant mass and constant pressure. Then we apply the equation again. V2 over T2 equal to V1 over T1 imply we have V2 over 88 plus 273 equal to 100 over 27 plus 273, and the new volume of the balloon will be equal to 120 cm cube, which is larger.